Hello, welcome to this lesson in the chemistry tutor. We're going to continue doing reaction stoichiometry that involves gases. I think they're a little bit fun actually because you get to do reaction stoichiometry, but you have a different element of it to it that we haven't tackled before, and that's involving the gases. So keep in mind that it's very common for you to have to use PV is equal to nRT somewhere in the solution here. All right, now for the first problem that we're going to do here, we'll use the following reaction: 2H2 gas plus O2 gas. Very common reaction, right? 2H2O, and that's a liquid. Now this is balanced. You can see 4 hydrogens, 2 oxygens, 2 oxygens. Okay, so the question is, how many liters of hydrogen gas are needed to react completely with 6.00 liters of oxygen gas to form H2O liquid, which is liquid water, at a constant pressure and temperature? The only thing that's really important here is for you to note that it's constant temperature and pressure. Notice it did not tell us it was at STP. It didn't tell us what the pressure or the temperature was, but that doesn't matter because all that matters is you're allowed to use volume ratios for the gas components of reactions as long as the temperature and pressure are constant. So when you look at this reaction, not even considering the gas law part of it, you know that this is 2 moles of this plus 1 mole of this yields 2 moles of that. That's how we've been reading it so far. Now you've expanded your knowledge to know that since these are gases and everything's constant temperature and pressure, you can also read this to say 2 liters of this plus 1 liter of that is going to react in that ratio. Notice that the water that's produced is a liquid. So obviously you can't use this as 2 liters of liquid. Using the volume ratio thing, that only applies to the gas components of the reaction. But this is an important thing for you to understand, is that even though there's a non-gas here, you can still use volume ratios for the gas components that are present. So it doesn't matter if you have solids or liquids running around, you're still allowed to use that for the gas components that are present. So it says we start with 6.00 liters of oxygen gas. And the question says, how many liters of H2 are needed to react with that? So because we're going from oxygen, we want to know how many hydrogen. We know that we're locked in a 2-to-1 ratio, and we can read that as in terms of volume, okay? So we know that 1 liter of oxygen gas reacts with 2 liters of hydrogen gas. That's the ratio. The liters of O2 gas cancels with the liters of O2 gas. So what you do is take 6 times 2, and you're going to get 12. You can just round that, drop all the decimals, 12 liters of H2 gas. Very simple problem. You just read it as if it were volume ratios, which is what it is when you have a constant temperature and pressure. It does not matter if you have something else running around your reaction there. You start with liters. If you're trying to find liters, the problem is very, very simple. Now for the next problem, it's not quite so simple because we're not really asked quite such a simple problem as we've done right here. So let me first write the reaction down for our next problem, which is the following: 2KClO3, and that's a solid. That decomposes to 2KCl solid plus 3O2. Let me go ahead and get rid of this like that, 2 gas. Now the reason I'm throwing this in here is so that you understand what to do when some of the reaction has other components other than gases. In this case, we only have 1 gas here. This is balanced: 2 potassiums, 2 potassiums, 2 chlorines, and 6 oxygens. So the question is, how many liters of oxygen gas are produced by decomposing 18.5 grams of potassium chlorate, that's what that is, at 150 degrees Celsius and 750 millimeters of mercury pressure? Okay, and then we have the reaction here. So the number one thing for you to realize is that we only have 1 gas component in this reaction. So yes, everything's happening at a constant temperature and pressure, but we only have 1 gas. So we can't use volume ratios like we were able to do in the last couple of problems, because we don't have, you have to have at least 2 gases in order to have a volume ratio, right? For gases and these types of things. In this case, we only have 1 gas present. So we can't say 2 liters of this to 3 liters of that, or 2 liters of this to 3 liters of that. You can't do it because these are solids here. This is a solid and this is a solid. So it's a little bit of it's not really a trick question, but it's the kind of question that you'll get on a test. Some students, believe it or not, will start trying to say that 2 liters of this goes with 3 liters of that. You can only do that when you have at least 2 gases that you're comparing between to get a volume ratio. But What we can do is use all of the other knowledge, all of the other pieces of information we know about the problem. So for instance, the mass of KClO3, potassium chlorate, is going to be potassium, which is 39.10, and then chlorine, 35.45. And then we have 3 oxygen, so 3 times 16. All right, so when we do this and we have 3 times 16, we add everything together, you get 122.55 grams per mole. All right, so the reason I'm doing that is because ultimately you're going to need it. It's asking how many liters of oxygen are produced by decomposing 18.5 grams of this reactant. Okay, so if you're unable to use volume ratios, you have to do a little bit of thinking. How can I get to an end game where I figure out how much product I've produced, how much oxygen in this case I've produced? I know how many grams of this I start with. I now know how many grams in every mole of this, so I can convert to moles right away. And then I know that this produces, in the ratio, 2 moles of this is required to evolve 3 moles of oxygen gas, not liters, moles, because these coefficients are always molar ratios. And so then I can get to the number of moles of oxygen gas. And then I'll have to figure out where I go there, but at least I've got close to the answer. In other words, it's asking how many liters of O2 gas. I'm not quite there yet, but at least I know how many moles. So let me at least do that much. So if we start out with 18.5 grams of KClO3, potassium chlorate, all right, and I know that there's 122.55 grams per mole there, then 122.55 grams KClO3 for 1 mole of KClO3, like this, okay? And the reason we write it like that is because we have grams canceled with grams. Now, if we do the calculation, we know how many moles of this we have, but we know that we go to a ratio of 2 to 3. So 2 moles of KClO3 react to produce 3 moles of O2 gas, because they go into that ratio. They react according to that ratio there. Now, again, this is not the answer, but it's getting a lot closer because at least we know how much oxygen we produce in terms of moles. So if I take and do 18.5 grams times 1 divided by 122.55 times 3 divided by 2, I will get 0.226 moles of oxygen gas. So we're close because the problem says how many liters of oxygen are produced by decomposing 18.5 grams of the reactant potassium chlorate. And also it tells us 150 Celsius and 750 millimeters of mercury. So what do you think you do next? We know how many moles are produced. We're asked to figure out how many liters are produced. Okay? So you need to start thinking about the ideal gas law. It's a gas. I know how many moles I have of this gas. I also know the temperature and the pressure of this gas because that's given to me. So PV is equal to nRT. I should be able to solve for how many liters of O2 I have. So start thinking about the magic guy we've been using all this time. PV is equal to nRT. And so you start writing down everything you know. The pressure is what? It's given to us in the problem, 750. But it's given to us in millimeters of mercury, which really is not a great unit of pressure because the gas constant is not really compatible. At least the version of the gas constant we've been using is not really compatible with that. So what I want to do is convert this to some other unit. Let's convert it to atmospheres. 1 atmosphere is 760 millimeters of mercury. We learned that before. We cancel this with that. So take 750 divided by 760 and you get 0.9868 atmospheres. Okay, so this is the pressure as given to us in the problem. The volume is what I'm trying to find, the volume of oxygen gas. Okay, the ideal gas or the universal gas constant, we're going to use 0.082058. The reason we're using that is because we're going to be dealing with liters, atmospheres, moles, Kelvin. So liters, atmospheres, moles, and Kelvin, like this. And notice this is already an atmosphere, so I'm able to use this guy here, and I'll get the volume back in liters. The temperature was given as 150 degrees Celsius, which, as you know, you don't ever want to use in a gas law, so you just add 273.15 to that. And when you add these numbers together, you get 423.15 Kelvin. All right, so we're ready to really to rock and roll, because now we have PV. I've already calculated in. This is the number of moles of gas I have. That's already given up there. I know R, I know T. Okay, so PV is equal to nRT. P is 0.9868. Volume of the gas is what I want to know. The number of moles of the gas, 0.226. That's N. That's R, 0.082058. And the temperature, 423.15. 423.15. And that's in Kelvin. So everything is compatible. So again, on the left, 0.9868 times V. Nothing really there. But on the right-hand side, we just multiply all these numbers together. And what I'll get is 7.847, like that. So in order to find the volume, I just take this number, divide by this one, thereby moving it over there, and you'll get 7.95. What unit? It's going to be the unit of liters. And what are we talking about? Oxygen gas produced. Okay. The reason it's liters is because the universal gas constant we used was liters atmosphere moles Kelvin. Pressure we used was atmosphere, temperature in Kelvin, and we use moles. Therefore, because we're using this, we're going to get a volume back in liters, 7.95 liters. So again, two different kinds of problems. If you have at least two gases in the reaction, then the mole ratio that governs those gases, assuming you have constant temperature and pressure, can be also used to be volume ratios, which is what we did in the first problem. In the second problem, we would love to do that. The only problem is we only have one gas. So you can't have a volume ratio with only one gas. You need at least two gases. So we have to go a different direction. And we see that we know how much of this we start with in grams. We figured out how many grams per mole it was, and then we know the mole ratio from this to this. So we figure out how many moles of oxygen we produce. And basically that's N, number of moles. And we use PV is equal to nRT to back calculate the volume in liters from that. So some problems you'll be able to use a volume ratio, and some problems you won't. It's going to depend on the problem. It's not cookie cutter. When you get into chemistry, the problems, they get a little different sometimes, and you can't just say, oh, do them all the same way every single time. You have to apply what you know and practice, 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 practice. So make sure you can do all of these problems. Follow me on to the next lesson. We're going to get a little more practice with stoichiometry and gas laws. And then we'll learn about a few other things in gas laws that are extremely important as well.